Well, good evening, ladies and gentlemen. First of all, I'd like to extend a warm welcome, as usual, to members of the Heritage Society of Engineers Ireland, but also on this occasion to members of the Structures and Construction Division and to members of the Republic of Ireland Institution of Structural Engineers. I have to first of all just point out security arrangements in the event, very unlikely event, that the hot air generated by the discussion causes a fire or something like that. But it's the way you came in and on the right there in the corner, provided that the door is unlocked. But also can I ask you to just switch off any mobile devices or switch them to silent. Thanks very much. The lecture this evening concerns one of Western Europe's biggest conservation projects, the complete refurbishment of St Mel's Cathedral in Longford, which, as you know, was gutted by fire on Christmas Eve 2009. The project is now nearing completion, and our speakers this evening are structural engineers Kevin Fay and Jonathan Macauley, and indeed their colleagues, and they will discuss the challenging restoration work, in particular the recreation of the cathedral's historic roof. I'll just say a word or two just about Kevin and Jonathan, because I haven't details of their colleagues. But Kevin is a director of Gem Purcell Ltd with overall responsibility for the conservation and restoration project, and Jonathan was responsible in particular for the specialist timber design of the large span roof and ceiling structure. So I now invite Kevin and Jonathan and their colleagues to present their lecture. Thank you.
Good evening, everybody. I suppose the reason we're here this evening, I suppose, is in relation to St Mel's Cathedral. So I'll just start in relation to the actual project itself, and literally maybe the topics that we'll actually discuss here this evening. Just maybe have a brief introduction in relation to the project particulars and into an introduction to Gem Purcell and who they are. I've included a brief history in relation to St Mel's Cathedral itself, and then a few slides in relation to the extent of the actual fire itself. And then I've gone to look at some of the stonework, particularly maybe a small section on the restoration or the replacement of the blue limestone columns. The topic has been covered before, so I'm just going to maybe just slip through it quite quickly. And then on to the main reason we're here is the historical roof of St Mel's Cathedral. Gem Purcell literally very much involved in a very intricate design and detailing of the actual roof. And then into the actual, if we have time, I've a couple of slides in relation to some of the other restoration works of interest in the actual project itself. So maybe just looking at me starting off with maybe some project particulars. The client is St Mel's Diocesan Trust, and the design team headed up by Project Management, Interactive Project Managers Limited, and then the design team being Fitzgerald Cavan and Partners, Punch Consulting Engineers, Arab Consulting Engineers, and then Carrick Conservation, and then ourselves as being the main contractors. Gem Purcell, literally, who are they or what are they about? Basically, the Gem Purcell are a collaboration between Gem Construction and Purcell Construction, who were formed literally, in relation to the restoration of St Mel's Cathedral. Both companies literally have extensive knowledge and experience on large-scale conservation projects themselves. They bring over 55 years' experience, and literally have listed out some of the actual well-known landmark buildings which Gem Purcell have completed over their time. Gem Purcell literally, we're committed to actually the restoration of St Mel's Cathedral, noted as being one of the largest restoration projects in Western Europe. And I just have then a small caption at the end. Literally, was something that I thought was kind of very poignant. It was actually a quote from the late Dr. Richard Hurley, who was a part of the project at the very, very outset and sadly passed away. But he had a vision for St Mel's Cathedral, which literally has been continued by Fitzgerald Cavan and Partners very much later true for the whole project itself. And he said, our aim will be to deliver a restoration project that protects the historical heritage of the cathedral's past, but yet reflects the contemporary pastoral aspirations of the future. I think it's actually, I think when you see the finished cathedral, hopefully it'll be reflected. I'm not going to go through much in relation to the history, but just that the St Mel's Cathedral itself first started in 1838 and continued right up to the fire in 2009. So I suppose what's happened in the last 5 years of St Mel's Cathedral will be the next chapter in the history of this landmark listed building. Again, there's been 3 architects involved in St Mel's Cathedral since its conception, and again, us continuing on the history, Fitzgerald Cavan and Partners will fit very proudly as being the 4th architects of this building as it goes into the next 100 years. So again, St Mel's Cathedral, just a couple of slides on what the building actually looks like from the era of the original photographs of St Mel's Cathedral, and then going through to some more modern day photographs itself. So then we get to the fire itself and why the fire actually happened. Just after 5 a.m. on Christmas morning, there was smoke seen coming from St Mel's Cathedral itself, and it was due to freezing cold weathers of -8 degrees outside. The boiler in the cathedral had been running for about 17-18 hours on Christmas Eve, and due to prolonged periods of combustion materials, it's thought to have they've accumulated in the chimney of the original St Mel's Cathedral. As long as the burners were running, these materials were deprived from oxygen, but when the burner was switched off after midnight mass, the natural drafts allowed ingress of oxygen, causing the combustion materials to ignite. Basically, it was a chimney fire. The chimney was fitted with inspection chambers, and it suggested that the burning embers escaped from the chimneys into the sacristy, where it spread into the interior of the cathedral itself. So this is what people woke up to on Christmas morning in St Mel's Cathedral. Pretty much a series of slides showing the actual devastation that was caused to St Mel's. And this is what the aerial photograph of January 2010 showed of St Mel's, and in particularly, you'll notice the topic tonight, the roof, it's non-existent. The fire then, and literally what the result of the fire itself, I suppose the roof structure and finishes were 100% completely destroyed. The ceilings and practically 100% of the decorative lime plaster, the structural stone columns, the decorative stone pilasters, the timber floors, the sanctuary, extensive damage to the external ashlar and cut stone, extensive damage to the stained glass windows, and then pretty much all internal finishes, including the original or the organ, St Mel's History Museum, and the internals of the Campanile bell tower loft. So again, just looking at some of the close-up external images of the building just after the fire and what was actually left of the building. So I mean, you can see that the main floors of the transept and the side aisles and the main nave are completely gone. There were timber floors, and they've fallen into the actual crypt below. You'll actually see what's left. I mean, you'll see the state of the actual blue limestone columns, which it's amazing that they actually are still standing at all. And then you'd see more pictures of the actual columns themselves, and you see the extent of, I mean, it's the amount of stonework in that. And again, this is the west side aisle. You can see the altar at the top, and again into more photographic images of the actual, just what it actually looked like. So this is what was left as a challenge for everybody. The reason I've shown this slide is just, I suppose, is a bit on the side, is that even with all the fire that happened in St Mel's Cathedral, where I believe the temperatures reached in excess of 1,000 degrees Celsius, the marble altars that crystallised literally and were sugared, but through it all, one oil canvas painting survived. Why, nobody knows, but the painting is currently being restored and hopes to be back in St Mel's Cathedral in the next 5 to 6 weeks. Just very quickly then through the actual, because I suppose where we are this evening, it's in Engineers Ireland, I thought just that I'd mention briefly the actual restoration of the columns themselves. There's 28 solid blue limestone ionic columns, structural columns in St Mel's Cathedral. You can see them here highlighted in blue. And we were allowed to carry on these works at the very outset without planning under Section 57. The reason why the columns failed was because originally when the columns were made, they couldn't get a seam of rock in the actual quarries high enough to make the actual pieces of the column drums. So what they did was they actually turned the columns to 90 degrees and actually carved the columns perpendicular to the actual way that the stone was laid down. So the horizontal bedding of the sedimentary rock was one of the reasons. The use of local limestone quarry and U-turn forms, and then the rock seams weren't deep enough to form the column drums. The intense temperatures that had reached in the fire, believed to be in excess of 1,000 degrees, the extent amount of water that was used for the fire, and then the freezing temperatures. You had this kind of freezing, hot and cold, and basically what happened was that the actual column started to split vertically. The challenge of actually producing the new blue limestone columns literally was a feat in itself. The columns had to be structural, they had to be aesthetical for the architect, and they had to match exactly the existing columns that were replaced within the cathedral itself. Stone Developments, which no longer exists, they were given or awarded the actual contract to supply the blue limestone columns. And this is just a picture of Old Lacken, where actually the stone, where it came from. It's amazing to think that literally, because of the structural importance and literally because of the aesthetical importance of the columns, there was 10,500 tonnes of blue limestone quarried, and out of that there was 675 tonnes is all that we got out of it in terms of St Mel's Cathedral. And that was literally to do with the blue limestone columns, the actual pilasters, the copings, the window surrounds, the padstones, and the replacement corbels, the campanile. So it's quite an extensive amount of actually stone that was actually quarried in order to get the actual columns out. But you'll see literally the level of detailing that's going into the columns themselves. Literally a few slides are just a level of hand carving craftsmanship. That was all thankfully done in Ireland, where we still have the skills to actually to carry this sort of actual work itself. You can see the egg and dart at the top of the columns. I mean, all of the columns were supervised literally by Kerry Conservation and by Fitzgerald Cavan and Partners, who took meticulous attention to detail, literally, and visited Stone Developers to ensure that every column was exacting in terms of its appearance, that the calcite lines were kept to a minimum, and that obviously, of course, that the structural requirements of the column would actually stand up to actually the challenge they had in front of them. The last column here is kind of slightly unique as a column drum. It's actually made from two pieces, because originally when the columns were being installed, there was no roof building, so they could have actually placed each column drum down as it was intended, and then with the last capital stone, and then take the actual masonry structure on above that. But because we had in St Mel's Cathedral, we had to remove the existing columns and put them back in place. The only way of getting the capital stone back in place was actually physically slide it in on rollers, because we had to support all of the masonry structure above it, and you'll see some slides later on to that effect. So just giving you some typical dimensions of the actual columns themselves. They're about 8 metres high. And again, this is just a quick sequence of how we actually went about taking out the columns and putting them back in. It hasn't changed much since the original columns went back in. I mean, we had the putlock stone at the top of the column. It really starts the stringing point of the actual masonry arch, and we had to actually support the putlock stone in place, remove the existing column completely underneath, and then replaced in the new stone column, bit by bit. I mean, the column drums, as you saw in the original photographs, they were so badly damaged that if you had to touch the columns at all, they would actually disintegrate. So we had to wrap and strap them, each column, and build a structural scaffolding system around each column in order to take the columns out and replace the columns. Again, which is done by pulleys and chains, because there was no other mechanism of actually doing it. So you see the amount of strapping that's on a column, and the actual, like, it's probably in a state of collapse, the column itself. And literally, when we actually took a column outside and took the strapping off it, the column actually just broke into pieces on the actual ground. So for safety reasons, I mean, it was very important that we actually strapped every column. I mean, there was initial strapping, but then we're actually taking out the columns themselves. We further strapped them again to ensure there was no issues. So this is trying to separate the actual the top column drum from the capital and the putlock stone. And when we released the columns, you can imagine an 8 metre high column of individual drums. It became very unstable. So we had to support each of the columns with a scaffolding system around the column to try and remove it. So eventually, bit by bit, each column came down section by section and was taken out on skips outside. And then you've got the new columns and going back in again in the same manner. A lot of it manpower, piece by piece even. We had to ensure that obviously the columns had to line up exactly with the striking point of the arch above and the putlock stone. So each column literally had to be set back up bit by bit and lined back in by pulleys and chains. There's actually a lead sheet between each column drum to give the exact joint that's required between the actual column drums themselves. And this is the way it was done traditionally. And we actually took out the original lead sheets from the columns when they were being replaced. And actually, the original people who installed them had engraved their names on some of the lead sheets, and some of them have been saved. So again, you can see the columns going back up piece by piece until we get then to the top column drum, which again was rolled back in by just traditional methods of blocks and pulleys and actually rollers getting them back into position. Then when the column got to the top, because again the old building, there was a gap at the top of each column where there would have been a fillet stone, but everyone was different, so they were all site measured on site to exacting tolerances, put in position, and then we were allowed to put a pressurised grout in at the top of the column to hold it in place. So that's the first finished column back in situ. Again, this is just some images then of some other external stone finishes. So then we get into the actual roof structure then itself of St Mel's Cathedral. The roof of St Mel's was originally designed by Punch Consulting Engineers, and it was a modern timber and steel structure. It consisted of laminated cruciform timber rafters, horizontal steel beams, and a curved steel channel to form the profile of the lower barrel vaulted ceiling. And as part of the planning objection, and Board Penala granted the decision that the new roof had to be designed and manufactured using timber trusses with traditional methods of mortise and tenon joints, cotter, jibs and pins. So the only dispensation that they allowed was that the bottom chord member of the truss could be a glue laminated beam section because of the span, and obviously trying to get maybe a single piece of timber of that size and dimension that works structurally. So basically Punch then Consulting Engineers in consultation with Fitzgerald Cavan and Partners went back and looked at a new design using these criteria and come up with using the traditional queen post trusses for St Mel's Cathedral. So I just have a slide here of what the original roof would have looked like before that on Board Penala decision, and a cross section what the roof was originally meant to look like. So then we get into the actual roof itself. It says Gem Purcell. We appointed Gem Joinery, who were a local specialist joinery company, to manufacture and install the bespoke structural timber trusses. Gem Joinery literally are a subsidiary of Gem Group, and they're one of the largest specialist joinery companies in Ireland, located in Longford with offices in Dublin and in the UK. With over 30 years' experience in designing, manufacturing and installing bespoke joinery elements, the company had undertaken many significant projects in value of over 4 million, including the recently acclaimed London School of Economics with Irish architects O'Donnell and Toomey. Gem Joinery said they had never designed or installed or even manufactured queen post trusses before, but the techniques involved in actually manufacturing a truss they have done on many projects in terms of the mortise and tenons joints. So literally it was a case of actually scaling it up to a structural design that was capable of doing St Mel's Cathedral. So then Design ID, they were consultants specialising in timber engineering that were appointed by Gem Joinery, and they first became involved in the project in February 2013. And it's just noted here that literally it's kind of fortuitous because the previous day they'd already installed queen post trusses, not of the same size or scale, but in a job in the north of Ireland. So again, initially design and the concept and primary timber roof structure was prepared by Punch Consulting Engineers, and literally worked through it with Fitzgerald Cavan and Partners, or Fitzgerald and Partners, to achieve the overall design. So basically that design then was brought through the whole way through into the actual structure itself. So just going back to maybe in terms of the challenges then that faced the actual roof structure itself, St Mel's Cathedral, it's not a new building, it's not a modern building, so we had to deal with the anomalies within the actual building itself. I suppose maybe no one had ever foreseen the amount of maybe variances that were actually in the original structure. So when we got up to eaves level itself, we carried out a complete total station analysis of the actual eaves level of the cathedral, and I suppose we weren't expecting what we actually found. Literally, first of all, there was a varying height and eaves level across from the nave on grid lines E to F. So you see here grid lines E to F. So basically the length along each one of those grid lines varied up and down as you went along the actual length of the cathedral itself. And because of the historical nature of the building and the coping, so they had to go back on the way they were originally. There was obviously then a varying height across the actual grid lines from east to west across the nave. So again, going across from grid lines E to F, the actual the wall plate, I suppose, height or east height of the building, that also was at different levels. The nave, again from grid lines E to F, they weren't in parallel, which meant obviously then we're going to have varying span widths. And to make matters worse, then there was original vertical slots in the original nave walls of the cathedral itself, and because it was a listed building, it was felt that we had to reuse these slots to put the trusses back in the original locations where they were originally. But these slots were up to 400 millimetres apart when you actually viewed from one side of the cathedral to the other, which meant that the actual trusses had to go back in at a skew across the actual cathedral. So if you see on this slide here, the trusses actually didn't go back in parallel across the nave, but they went in at a skewed angle, which meant that an awful lot of things that followed afterwards were skewed or literally in varying in length, which added just another layer of complexity and a work to the actual project itself. They were actually all the items that were kind of the variables within the actual, but there was also then the fixed parameters that the actual, because we're using the blue Bangor slates, later we had a maximum pitch of 25 degrees which we couldn't change, or a minimum pitch of 22.5 degrees. and obviously a fixed horizontal ridge line of the cathedral. And Fitzgerald, Cavan and Partners were very much insistent that these parameters were actually met as part of the actual roof design. So we looked at a number of options of how we were going to actually to get this roof to work. And we initially looked at installing the roof trusses horizontally across the actual building itself. But because of the varying height of the actual eaves level, up to 90 millimetres, this wasn't an option. And obviously it was going to mean that if we had one side lower, we're going to have to maybe cut back into the actual coping stones that had been installed. So to achieve a solution which addressed these parameters, the trusses themselves were installed off level. So we actually physically rotated the truss. We designed the truss, and then the truss was actually rotated to 90 millimetres. But in doing that, we changed all of the actual roof pitches of the truss. So then we had to go back and redesign the actual rafters of the actual truss to make sure that when it was turned into 90 millimetres along the length of the cathedral, that we're actually meeting the pitches required by the architects. So when we did this, then we actually had to look at also the ridge line, the constant ridge line. So again, we looked around the building, and we surveyed it again, and we found that the widest span in the cathedral was in grid line 5, which is back at the end of the building. And again, we decided that we're going to fix the ridge line at that point, given the highest point of the common rafter, and that point then was used right down along the length of the actual building itself. And to try and accommodate that down to the actual building, we actually had to pack the actual purlins themselves with hardwood timber packers. So in essence, between each grid line of the actual building, we had a constant ridge line, but we had a varying pitch on either side of the cathedral, literally, that was fixed between those grid lines. So in theory, the actual roof of the cathedral is actually slightly going up and down as you go down along the cathedral, but the ridge line is constant. But you don't see this wave within the roof because it's so minimal. We're only talking about a couple of degrees from end to end, but it is there, and it does exist, and that was the only way that we actually could recreate the actual cathedral roof structure back to the way it actually was. So the main roof structure in itself, it consisted of it was 900 by 600 Penryn country grade blue blanker slates on 35 by 50 treated counter battens and 22 by 50 treated battens on Tyvek breathable mare on 80mm marine ply, and then we had the 150 by 44 common rafters and the 200 by 150 purlins, and then we had the traditional queen post trusses themselves. The truss itself was manufactured using a combination of Douglas fir, German spruce, and then glue laminated bottom cord as allowed by On Board Penola. The original timber for the trusses, they know exactly where it came from. It came from a wild-grown forest just in northern Siberia. The timber was actually shipped to St. Petersburg and actually came into Ireland, so they know exactly the species of timber that was used in the original. But that was a very slow-growing timber, and obviously had the structural capacity that literally some of the modern timbers that we have now doesn't have. So then, looking very quickly at the actual queen post truss itself, because Jonathan will go into more detail into the actual design of the queen post. But there's 13 queen post trusses in total, and that gives you some level of the size and scale of the actual truss itself. And again, we'll come back using some of the traditional methods with cotters and jibs and pins and mortars and tenons, which Jonathan will go through, and I will go through in greater detail. And then we end up with the structural elements of the truss itself. One of the unique probably features of the way that the roof was designed, which the design I do will go into in more detail, and it was something that Punch Engineering specifically had allowed for in the way the roof was to be installed, is that when the queen post trusses were put in initially, they wanted the roof structure above that to be completed first. So when the queen post trusses went in, the roof structure, as in the purlins, the common rafters, and the roof loading, that went onto the roof itself. So they got initial deflection in the queen post trusses, and only after the initial deflection took place were the haunches engaged and installed into the actual truss. So that initial deflection was already in the truss. So the only additional loading that was going to come onto the truss at that stage was going to be actually snow load, and we also then would have the actual ceiling load from below, from the barrel vaulted ceiling itself. So again, just a couple of images in terms of the size and scale of the actual trusses themselves in being manufactured in Gem Joinery's facility in Longford. Again, a couple of more pictures of the queen post trusses, and then into the actual just ready for installation on site itself. The trusses, getting the trusses then into position in St Mel's Cathedral in itself was an actual challenge. One of the very first things that was done with St Mel's Cathedral after the fire was to put a temporary roof structure onto the building to protect the remaining elements of the structure. But with the roof structure in place, it challenges in getting the new roof structure in place. We couldn't take the temporary roof covering off the building because 12 months previously, excuse me, we had started the lime plastering contract in St Mel's Cathedral, and because the extent of amount of the lime plastering contract and the amount of it, those works were very advanced at this stage because of the drying out period of them. And so we couldn't take off the temporary roof structure because all of the actual nave walls were actually fully plastered at this stage before the roof went on the building. So we had to come up with an idea of actually trying to get the roof trusses into the building. So we used the blue limestone coping stones, and we installed, I suppose, a railway track system down both sides at eaves level within the actual St Mel's Cathedral. And we designed a special trolley that would sit on this rail track system. And we literally manhandled through a crane. We opened a small slot in the roof of the cathedral, and we lowered the trusses into the roof. We put them down onto the two trolleys which were made going down both sides, and each one was actually physically manhandled into position on site, truss by truss. Then we had a wench system, pulleys and chains, that lifted it off the seating arrangement and lowered it down into a slot in the coping stones to receive it. So just have a small video here that maybe Jonathan is going to maybe show up on the screen just of the installation itself. So again, it's just to give you an idea of maybe the size and scale of the roof trusses being lowered into position. It's a slightly shaky camera, but it'll give you some sense of literally. One of the things on that design idea had to look at is actually how we actually lifted the truss in position. It wasn't a case of actually just lifting the truss from the top, or we would have actually affected the actual top joint. So they actually physically had to do a calculation and checking literally the support points of actually lifting the truss in this mechanism and supporting it from the bottom to ensure that literally we didn't cause any damage to the truss when it was actually being guided and actually lifted into position. So you can see slowly but surely each truss comes in one by one. So we had a scaffold down both sides of the building itself, and we actually just walked it down. You can see the two I suppose timber formed track systems that we had down both sides of the actual cathedral itself. So eventually this does make its way into the trolley, and then it gets into position. So it's just to give you an idea of the actual of the truss being installed. So again, just before I hand over to Jonathan or to Niall, just a couple of just some of the level of detailing and bracketry involved in terms of the joint connections with St Mel's. And again, that's the slot in the wall is the original putlock hole where we had to install the truss, and then the slot notched out of the blue limestone copings, and then just some images then of the trusses of the main nave in situ on site. Again, just some images then here we had some other the hip arrangement of the other trusses supporting it, and again there's just the level of complexity of how it actually went together. And then you can see the haunches here locked in position. At that stage the actual roof would have been loaded with the blue Bangor slates. And you can see in the background there, which I'll talk about slightly in a minute, the curvature of what will be the barrel vaulted roof itself. And then this is the finished roof of St Mel's Cathedral with the 600 by 900 blue Bangor slates. The slates themselves were made specifically for the project, and they were the original slates that was on the roof of St Mel's Cathedral. They actually have the records of the slates on the roof itself. So again, just given the finished roof of the main nave, the side aisle and the transept of the roof. So I'm now just going to hand over to Jonathan, who's going to talk a bit more of the engineering aspects of the truss itself, or to Niall, and literally I'll talk to you again in a second.
Thank you, Kevin. So I'm just going to give you a very brief introduction to who we are, Design ID Consulting Limited. So we're a, a practice of structural engineers who work with a diverse range of projects and materials. We do lots of general engineering work, and we also tend to take on a lot of jobs that other people don't want to do, and we usually find out why they don't want to do it when we're fully involved. So just a very quick summary, a few example projects of what we have done. This was the Giant's Causeway Visitor Centre, which I'm sure most of you are familiar with. We were responsible for the design of the post-tension stone columns. And that was a technique that's rarely been used in Ireland or the UK. We do general engineering, as I said, industrial commercial buildings. This was a factory for Caterham cars over in East Anglia. And then we do quite a bit of conservation engineering. This one of particular interest, it's Crumlin Road Jail in Belfast, which has a checkered history, and it's one of the wings is currently being converted into a distillery for Belfast's first whisky distillery for, I think it's over 150 years. So quite an interesting one to be involved with. And another big aspect of our work is designing timber structures, both contemporary modern techniques and also using traditional techniques. And as Kevin mentioned, when Gem Joinery first contacted us, we had just completed the design of these particular queen post trusses for a project at Larne Market Yard in County Antrim. So very, very similar in the design, scales slightly less. They were spanning about 8 to 9 metres. But I think it was a relief for both Gem Joinery to find somebody who had worked on similar type designs, and also it was good for us to have a chance to work on a prestigious project such as Longford Cathedral. So I'm just going to pass over to Macaulay and Niall O'Grady, who was the project engineer doing the actual detailed design of the roof trusses. And I'll come back in a minute and speak about the design of the Apse structure. Now.
Thank you very much, Jonathan. Good evening, ladies and gentlemen. Yeah, I am basically I'm going to go through the design of the roof structure and what was entailed. So, as Kevin would have already highlighted, there was a series of queen post trusses throughout the building. So, over the central nave, we had 11 Type A trusses, and then towards the front, then there was a more heavy-duty Type B truss. Basically, this was more heavily loaded because it supported the Apse ceiling. Then in front of that, then again, we had a Type Truss B1, which supported the hip raft, or the hip trusses, and the jack truss. It was, you can see there in the bottom right-hand corner, the flitch plate detail that we had to do to overcome the issues with shear at the support point. And then, as I explained, then that is the layout of the hip and jack trusses that are supported from Truss B1. Then on the side aisles, we have just some simple lean-to trusses, and then over the transept aisles, then there was some king post trusses. So that is the layout of the finish. That will be the finished of the main nave trusses. As Kevin explained earlier, you've got the haunches underneath that were required as part of this project to keep in line with what was originally in place. As Kevin said, the sequence of the application of the load was very significant here, because the haunches had the potential to exert a significant horizontal thrust onto the wall, which wouldn't have been acceptable or wouldn't have been in line with the original design. So in order to overcome this, the truss was first designed to take into account just the roof dead and live loads, and also an access load. So then after the roof was built, then the haunches were added, and then obviously the ceiling below was added and plastered. So the design and the analysis took this into consideration throughout all the stages. What we have here then is just a very simple breakdown of the main components of a queen post truss. So basically you have the tie beam, which restrains the rafters in place. And then you have the principal rafters themselves, which support the purlins. You have the queen posts, and then you have the straining sill, which in this case had a considerable force into it from the principal rafters. Then the straining sill sits on top of the tie beam, and the purpose of this is to reduce the shear load on the tenons of the queen posts. And then we had the struts then, which are to support the principal rafters and basically prevent excessive bending in the principal rafters. So I'm going to just then speak briefly about the joints. As with a lot of timber structures, and in particular traditional timber, the joints are very important. So main focus here was to obviously create joints that were going to be in line with current requirements and regulations such as Eurocode 5, and also that they were going to maintain traditional techniques. A key joint in these trusses would be the joint between the principal rafter and the tie beam, which is a mortise and tenon joint. The compressive forces in this were in excess of 33 tons or 330 kilonewtons, which was extremely high. So in order not to have too many bolts in place to take the load, we designed the timber for what it could take, and then only used the minimum amount of bolts to help to bring it in. So in the case, we only ended up with 4 number M20s to deal with such a high load. And then obviously the most important aspect of traditional joinery for this type of joint is the shoulder. So the shoulder is so important as this transfers the axial loading via direct bearing, and then it prevents shearing of the tenon itself. So that's the shoulder there that Jonathan's pointing out. So that recess, that shoulder there of 80 mil works to create direct bearing. So you can see on the slide over on the right hand side then how that the tenon comes in there, and if you didn't have the shoulder, the tenon would just simply shear off. So that's just some images of the constructed article, and you can clearly see the shoulder. And then on the right hand side you can see the stirrup, which would be in line with traditional methods. In this case it wasn't particularly needed because the bolts were doing the work, but it was required just to keep the general overall feel that the truss was in line with what would originally been used. Another very important joint then as well would be the joint between the principal rafter and the queen post. Again, there was 333 tons of a load onto the queen post. So the compressive stress in the queen post was calculated, and that could only take approximately about 35% of the load. So then the remainder of the load, we use a steel strap to take that through the joint. So we kept the strapping as slim as possible, just in order not to take away from the feel of the truss, and to actually make it keep in line with what originally would have been used. There wouldn't have really. So then the next joint then would be the joint between the strut and the queen post. So the strut, due to the forces from the principal rafter, the strut exerts quite a considerable shear into the queen post, both horizontal and vertical. So the straining sill, which is highlighted with the red arrow there, that's used to reduce the load on the tenon of the queen post. And then also here on this as well, you can see that the shoulder is in place underneath the strut, and again that helps to relieve the stress on the tenon, and also to keep the shoulder in place and stop it slipping. Again, that just shows the line of the horizontal shear across and how that the straining sill is resisting it. Again, that's some photographs of the joint. On the right hand side you can see the steel bracket that was used, and as Kevin explained earlier, at the top there it's fastened using jib and cotters, which would be the traditional way of doing it. The reason that the steel strap is used is because during the working life of the truss, the tie beam has the potential to shear the oak pegs, and we've seen in a number of cases where there hasn't been a steel bracket in place that the tie beam is actually fully separated from the queen post, and it's still standing, but don't really know yet how it was. So then just a more simple joint would be the joint between the principal rafter and the strut. It's just to highlight that wherever we could, we kept with traditional methods, kept it as simple as possible, and didn't introduce any steel brackets or straps unless we really had to. And you can see here again the importance of the shoulder and how that is used to relieve the shear and the tenon. So again, that's just showing the compressive force that's coming up onto that joint and how it's resisted by the shoulder. And then again, that's just Gem Joinery's work at the finished product. So then as well, this is just a layout of the hip and the jack trusses, which are supported on truss B1. An issue that we had during the analysis of it was that you see there the green arrow, which just highlights the self-weight of the trusses themselves. That self-weight, it just induced this horizontal minor axis bending on the bottom chord of the supporting truss B1. So in order to overcome this, we introduced slotted connections onto the steel bracket. Traditionally, this wouldn't have been the method that would have been adopted, but we felt that given the site constraints and given the nature of the project, that it was best to adopt this as opposed to using a sliding slate system or something similar that is often used in traditional methods. So again, that just highlights the fact there that bracket allowed that movement and stopped the minor axis bending of the supporting truss. So now I'm going to hand back to Kevin Fay, who's going to take us through the ceiling structure.
Just very quickly, I have a couple of slides here, just in relation to, obviously, unfortunately, I suppose as engineers, no one's ever going to see any of the queen post trusses or any of the amount of timber that's up in the roof of St Mel's Cathedral. Like so many engineering structures, they get hidden away. But below the queen post trusses, there's probably another complete timber structure that's supporting the actual barrel vaulted ceiling. And again, Punch Consulting Engineers and Fitzgerald, Cavan and Partners were very much involved with this element of the works, purely because we're trying to recreate the historical ceiling, I suppose, of St Mel's Cathedral. And there's a lot of constraints. You can see here at the lower end of the picture, there's the Diocletian window, and obviously the striking point of this in the cathedral was very important. And there was very little evidence, bar historical photographs, to try and piece together the true geometry of St Mel's Cathedral. And going back to the earlier problems in terms of the varying height and the varying widths of the actual cathedral itself, it proved its own challenges. So you can see it's actually made up of a series of timber sections. They're about 300 by 150 timber sections faceted around in the actual cathedral itself. And the only way we could try and do this on site, because of every grid line we went to was different in terms of width, Gem Joinery came up with a proposal of we actually made up a timber template that was actually offered up at every grid line of the cathedral itself. And we opened and closed the top section of this, I suppose, template. And every arch in the cathedral is different in the barrel vaulted ceiling. And this opened and closed as you went along the cathedral itself to try and create the true curvature of the actual cathedral. In between the 300 by 150 timbers, we had to put in the ceiling rafters themselves, and we had to come up with a bracketry system of actually doing that. And this particular bracket here, it was used because it can be rotated from 0 to 90 degrees and not affect the structural capacity of the actual fixing itself. So again, just a few photographic images. You can see the template in place. You can see the gap at the top. And in some instances along the cathedral, that gap was actually 0, and other places was up to maybe 200 and 300 millimeters. It varied along the cathedral itself. So again, you can see the amount of timber that's actually below the level of the of the queen post trusses. And to give you some of the section sizes, and this all had to be manhandled on site by hand. And again, it just gives the extent of the amount of timber work. And because we go back to of the truss originally, because every truss wasn't parallel to each other and they were skewed, every single piece of ceiling rafter, every one is a different length, and every single one of those had to be measured on site and cut to suit. Like, there's hundreds of them, there's thousands of brackets, and then the engineers wanted to brace it in terms of bridging. So literally all the bridging had to go in as well. So literally there's a huge amount of, and again, none of this is ever going to be seen by anybody, but it is up there. It does exist. It'll be covered up for the next 150 years. Again, just gives the size and the extent of the actual barrel vaulted ceiling. You can see a person there climbing up the side of it in terms of the amount of timber work that's actually involved in actually forming the ceiling itself. And again, you can see the size and scale of the timber. One very unique aspect of the actual ceiling structure, and probably in terms of the structural element of it, there was the least amount of information known about the actual structure of the apse ceiling itself. So no different than the nave ceiling, this beautiful ceiling which you see in front of you had to be supported in some way. And Design ID, again in consultation with Punch Consulting Engineers, and very much with Fitzgerald Cavan and Partners, because this was maybe, I suppose, a centrepiece of the cathedral. So in terms of recreating it, again, the limitations of how we achieved the finished ceiling had to be met. So Jonathan is just going to go through a very unique timber structure that was created above the level of this, which is self-supporting in itself, which I think is a very unique piece of engineering.
Thank you. Sorry, just bear with me. I'm getting slightly parched. So as Kevin mentioned, there were no records of the structure behind this ceiling, so it was pretty much a blank canvas for us from the start. Excuse me. One of the first schemes presented to us when we were brought back on board was an arched glulam structure, and being glulam, we felt it wasn't in keeping with what would have been the original design. So our thought process was trying to come up with a scheme that used standard timber sections to create an all timber structure in what may have been akin to the original design. So the concept we came up with were these bottom chords of the truss B and B1 toward above the apse. We created self-supporting timber arches. These were radial arches that required a temporary lateral prop at the top. As shown at the bottom end, I'll come to it later on, it took support off the radial wall. So there were 6 number of these. And then onto the timber arches, there were 4 lines of purlins. And then in turn, those purlins supported the rafters. So the support points highlighted here in red. At the base of each of the arch, we had a main support. That's the main support, and then a secondary vertical support here. And then again at the top, this purely took lateral load, so it didn't exert any load onto the trusses above. So I suppose one of the questions, why not suspend this structure from the timber trusses above? Well, at the stage when the apse structure was being designed, the timber trusses had already been installed, and they hadn't been designed to take any additional load from the apse ceiling. And there was little interest or enthusiasm for going in and strengthening what was already there. Plus we felt we could come up with a scheme that was self-supporting. So all we needed really to do was to resist the lateral load, and that was taken back into the bottom chord of the truss above, which I'll come to in a minute and show you how we dealt with that. So the primary supports for each of the 6 radial arches, we had, as I say, the upper support was the primary support, and that was supported off an existing ledge on the radial wall around the apse. So from what we could see on site, there were a couple of ledges, the main ledge being the upper one, and we felt again that must have been used in the original design, so we tried to design our structure in keeping with what was there. Down at the bottom, the secondary support was quite a simple galvanized steel shoe that was embedded into the wall. And then up at the top, so we had where all the radial arches came together. It's quite a complex arrangement and quite congested in reality. On the drawing, for us, it's probably quite simple. But when Gem Joinery had to install it on site, it was a slightly greater challenge. So again, that was the horizontal force reaction that was required up there. So the analysis model, we built a 3-dimensional model in an analysis package called Master Series. And we took into account, we analysed the first bay of the common ceiling rafters, just to ensure all the loading was being applied to our structure. From this model, we were able to generate a three-dimensional model in AutoCAD, and both the Master Series Analysis model and the AutoCAD model had quite a bit of intelligence built in. It allowed us to generate material lists for GM Joinery to assist in with the ordering. So for instance, the radial trusses, all section sizes used were 75 by 225, so standard timber sections generally available off the shelf. Then it came to the purlins. Again, the majority of these were constructed from 75 by 225, apart from the third row up, which we had to use 300 deep, which again, GM Joinery were able to source these quite easily. And then the rafters, again, they were 44 by typically 175. So there's nothing unusual in the size of the timber that was required. The overall structure, it was designed, every joint was designed as pinned, again, to make it a lot easier to construct, and the detailing was followed through to ensure that the bolts used actually enabled it to be pinned and act as pinned. Again, some of the material lists that we were able to produce from our three-dimensional model. Everything we did, it was because we were working for GM Joinery, it was to try and assist them in the construction. You know, it was a complex enough scheme to build, so the more information we could provide to make it easier, the more we did. Again, these were the brackets that were used to connect the purlins onto the side of the radial arches. They were cut from standard 150 by 150 steel angle profile. Again, we tried to keep everything standard, to keep it simple. So, going up onto the lateral force that was exerted from the top of the radial arches into the bottom chord of the trusses. So the blue line, that was a tie member that we used. So we tied. So the thrust was exerted here and was acting in that direction. So it was a 20mm diameter tie rod to connect back into truss B1. So first thing this would do would put the bottom chord in minor axis bending. So we come up with an in-plane bracing system using, again, it was 75 by 225. You probably get bored hearing of that. To take the forces back into the coping stone along here. So the joints at the edge of the coping stone, we had to ensure that the horizontal reaction was applied directly into the side of the coping stone. So the pocket that you would have seen in Kevin's earlier slides, we packed and fully grouted the gap between the side of the truss bottom chord and the coping stone. Again, the next joint in, it was quite simple flitch plates bolted onto the side of the existing truss. And then the centre joint, that's where we were able to connect in the tie rod. So some photographs of what the in construction radial arches and the overall structure actually looked like. So again, looking at the guy in the middle here gives you a sense of the scale of what we're working with. All the rafters were connected on to the purlins using just standard joist hangers. We could have done that without any joist hangers if we'd nailed on a timber ledger and rebate it or notched all the rafters, but as this was the final piece of the ceiling structure to be installed, the joist hangers had been used elsewhere, and we felt there was no need at that stage to be complicating the scheme any further. Again, a few different views. And that was just at where the radial arches came up and connected in. The steel flitch plates has been conveniently hidden. We trust that it was installed. Kevin. So then I'll just hand you back to Kevin to talk about a few of the other, well, to show you some finished photographs of the Apse ceiling. I suppose what we tried to do was design an elegant and simple structure that was in keeping with what may have been there before, and hopefully you'll agree that it was achieved in some aspect.
The next couple of slides, I'm just going to show. I suppose it's what's covering up all the engineering. It's everything that came afterwards, And I just have a couple of slides for both of the barrel vaulted ceiling and the Apse ceiling, just to see the next stage of literally what we took the timber roof trusses and took the ceiling structure and actually what resulted as being the finished product in terms of the actual St Mel's Cathedral ceiling below. So this is the, I said it was the original ceiling of St Mel's Cathedral, what was there before the fire. And this is an image from Fitzgerald, Cavan and Partners, just kind of recreating some of the actual design and detailing. So again, from the timber carcass structure that we would have seen earlier, we then had to proceed and actually start with the lime plastering works. And again, it just shows the extent of chestnut riven latting that would have been involved in all the downstands and of the ceiling. And again, the original lime plastering works, the first coat of plaster works on the cathedral, and then progressing through the downstands first, then into the coffered areas between the downstands, and then we start what you call it, producing some of the actual the lime plaster itself. And you can see then the works slowly but surely starting to build up with some of the Greek arches and some of the original features in the ceiling itself. The hole in the centre, it was formed. There was originally grills in the actual cathedral ventilating the actual roof space, but again, true to its form, because of the historical nature of the building, these were recreated so that they look the same on completion. Again, some of just the plaster work working through, and this again some of the actual the dental enrichments on the actual plaster work. And you now approaching what approaches the finished ceiling. You can see again in the image the grille being recreated all in lime plaster work, and then some of the very ornate decorative detailing that's quite large when you're close, but on the ground it's very, very small. And again, some images of the completed barrel vaulted ceiling from the actual ground, and that's the finished ceiling of St Mel's Cathedral, showing the barrel vaulted structure, and showing then in the second photograph there, it shows the apse structure itself, and then there's some more photographs of the apse close up and how it actually went from being the queen post trusses, then by the self-supporting timber structure underneath, and then followed through with the actual lime plastering works below that again. And again, just to give you a sense of size and scale of the amount of lime plaster work and the detailing involved itself. Just a couple of slides just going through in terms of the enrichments and the apse and the level of detailing that was again true to the original historic nature of the actual building itself. And then we arrive at what is the finished apse plastered ceiling. That pretty much concludes the presentation on the roof. There's one or two other quick slides just in relation to St Mel's Cathedral which might be of interest, and it's just there's some other slides there of some of the plaster work in the cathedral. This has been the main cornice of the cathedral. It's about a metre in height of the lime plaster work. The project itself, it's threw up a lot of skills and trades. Thankfully, we have and still retain here in Ireland. I mean, all the skilled tradesmen. That's actually running the actual cornice in the apse. To give you a size and scale of running a cornice, it's on a very large scale. The cornice in the apse, the actual curvature of the apse on plan, it's not a true curve, and it's about 5 varying curves or radius, and every time we had to move this jib on site and actually set up a new, and actually each one of those radius curves then were actually finished off by hand to make it look from the ground, it looks like a true curve, but in reality it's actually 5 individual curves. So again, it just gives you a sense of the size and scale of plasterwork and the amount of work involved in the restoration project itself. And again, just going through some images very quickly of some of the plastered arches and the decorative work and the craftsmanship that we still have in Ireland. The plaster work carried out by Macauley Plastering. Just going through some slides and some of this. So you can see actually at this stage of the project, the temporary roof is still on the building and all the temporary supporting steelwork. So when we were actually doing the actual roof structure, like all of this finished plasterwork that you saw in the previous photographs, that was all done and finished. So we just couldn't take the roof off the building and just leave it open to the elements. So hence it was done in a very methodical manner. And again, I've just a couple of quick slides just in relation to the restoration of the angels. Again, these are probably one of the only pieces of St Mel's Cathedral which were original, and there was 28 angels and 26 of them survived in some varying degree or other, and they were all restored and they've all been put back into St Mel's Cathedral. But again, it shows what was left and what's being created and put back in place. And again, it's just a build-up of the restoration works of just various elements which are of interest. Again, just there's some commissioned works then in St Mel's Cathedral. This is some of the Stations of the Cross, and these are all hand carved in bath stone, and all currently being installed in St Mel's Cathedral itself. I suppose from an engineering point of view, literally just maybe a piece aside, the techniques that were used. The altar in St Mel's Cathedral is one piece of white Carrara marble. It's about 8 tons in weight, but the floor of St Mel's Cathedral can't take the weight of it, the original floor. So this had to be brought into the cathedral on a again traditional methods. There was a railway track from the front entrance door right up to about 800 millimetres where it would sit on the final sanctuary slab, and it was traditional methods. We had to create an actual train track system from the door, bringing the piece of stone into the cathedral, and it was just pure manpower. Literally, a track system where we moved steel sections forward, and literally people either side of it, and it was pulled into position. Again, another piece of commissioned work is the organ, which, as it just turns out, has actually arrived from Italy today on site. The organ has been commissioned by a company called Piero Fatti in Italy, and the organ itself supports on a steel structure. This particular steel structure within St Mel's is unique insofar as that the organ manufacturers, they didn't want any deflection whatsoever in the steel structure to support the organ which sits on top of it. And Punch Consulting Engineers came up with a structure to assist in that, and this was all welded on site by coated welders, and every joint was X-ray welded to it, literally, when it was completed. And thankfully, the organ, which is currently now made, is the organ in production in Italy, arrived on site today, and it's currently been installed in St Mel's Cathedral. It'll take 4 weeks to install, and an extra 5 weeks to tune this organ when it arrives in the actual cathedral itself. Again, some of these are the traditional Harry Clark windows, which did survive the fire and actually have been restored and are now back in position itself within the cathedral. And then alongside that, we get, I suppose, the completely opposite or juxtaposed. These are windows, they're stained glass windows that have been designed by a monk in France called Kim En Young, and they were designed by Kim En Young, and they're called art glass as opposed to stained glass. They don't have any leadwork in it, and they were actually then made by a company called Derrick's in Germany and installed by Stefan Eitmann, a German company who installed these stained glass windows into the original openings. And then this is just literally where the cathedral of where it is currently at the moment. It's 9 weeks today until such time as the cathedral has to be finished. It's been televised live on Christmas Eve, so it has to be finished. So there's absolutely no pressure in trying to finish this project whatsoever. But we're 9 weeks from completing the project. It has been a pleasure to work on with Gem Purcell. I mean, a project like this just doesn't happen. There's a huge emphasis and effort on everybody involved, from the design team, from the people on site. I mean, this is a vision of Fitzgerald Cavan and Partners of what the cathedral will look like. And thankfully, it won't be a million miles away from this, hopefully, when it's open to the public in 9 or 10 weeks' time, literally. So it's it's been a pleasure to work on the project. It has some magnificent engineering challenges which has been overcome. The design team have played a huge important role in achieving it, but I think the craftsmanship and the workmanship of all the subcontractors who worked on the project itself hopefully will be a testament to the next 150 years of the lifetime and beyond of St Mel's Cathedral in Longford. So I'll pass you over to Kevin Mullery from Punch Consulting Engineers, who's just going to give a closing, and if there's any questions, and after that I'll gladly take them.
Good evening, ladies and gentlemen. I'm Kevin Mullery. I'm a Director of Punch Consulting Engineers, and it's my job this evening to give a vote of thanks. Obviously, I'd really like to thank the three speakers, Kevin Fay, Jonathan Macauley and Niall O'Grady, for their excellent presentation. I suppose you look at the finished product on screen, I think the building shell that Kevin Fay inherited did him no favours. The plumb bob has been around since, I suppose, the Egyptians' time. However, around Longford in 1840, I don't think the original builders at the time used it that much. The integration of primary structure, secondary timbers, decorative plaster, support structure in a space that was frankly out of level, out of line and out of plumb, that was where the magic happened. And I'd say congratulations to Kevin, to Jonathan and Niall, and I suppose the unsung heroes of Gem Purcell's Ronan Moore, Punch's Ger Neville, and the master plaster George O'Malley. And I really would say hats off to you for completing this. Now, we're here in the home of engineering in Ireland, so you're probably one of the more receptive audiences to the idea that the lads have indicated that and highlighted that this was an intensive structural engineering project. And while that is absolutely true, the success of a project like this comes from the effectiveness of a large group of people, that we're all working together. We have respect for one another's abilities, and we all have a desire to achieve a common goal. Now, of course, every team needs a captain, and it certainly was no easy job to keep the rest of us in line. Now, Kevin mentioned the late Dr. Richard Hurley, and he was that person for a time. However, the captain's mantle was certainly taken on and taken over by interactive project managers Niall Maher and Fitzgerald Kavanagh's Cullum Redmond. I might let Cullum and Niall fight it out amongst themselves for which of them had the honoured title of vice captain. But I suppose with 9 separate building contracts, 5 planning applications, and not to mention 2 trips to on board Planala, I suppose the success of a project like this is very much dependent on a long collaborative effort of a dedicated team. And finally, earlier this year, Kevin Fay, I suppose, kindly allowed the doors of St. Mel's to be open to view progress to the public, and the people of Longford turned out in their thousands and thousands. 4 years before that, Bishop O'Reilly, when faced with, I suppose, a badly fire damaged shell, he instinctively understood and was in tune with the people of Longford, and he said, "We will rebuild it." That vision is now nearly complete as Gem Purcell rebuild a sacred space where God can do his work. Thank you, and safe home.
Well, I'm sure you'll join me, well, you've just joined me anyway, in thanking the speakers for their very interesting, informative presentation and extremely well illustrated. I think the 207 slides is probably a record for one of our meetings. I think it's 207 it went up to. How you can do 207 in an hour, it's a little more than 2 every 30 seconds, as far as I can make out. Anyway, I'd now like to invite questions from and comments from the audience. And when you're speaking, if you don't have the microphone, please stand up because you'll be heard better. But I think there is a roving microphone around. Yes.
Hi, Kevin. My name is Georgina. I work for a scaffolding contractor, designing scaffolding, and the tender drawings crossed my desk a couple of years ago, and for one reason or another we didn't get the job. But when I saw this advertised, I thought I'd better come along and see what I missed, and I can see that I missed out on an amazing project. So you know, I'd like to say well done. It looked amazing, and one that a lot of people would have loved to be involved in, I'd say. Looked great. I just have a question in terms of the temporary roof. Did it get its support from the original walls? the original, the temporary roof they first put up.
Could you use the mic?
In between the arches, there's actually a steel structure.
Okay.
So the actual, they were primarily there to assist with the columns, but they're supporting all of the masonry, which is actually above the level of the actual arches, and they were also designed to take the load of the temporary roof. So the temporary roof comes onto the masonry above the level of the arches, which in turn goes onto the steel structure, which is in between. And we actually use that temporary steel structure to actually to support the scaffolding that you mentioned it.
Yeah.
Because it was one of the unique things that Gem Purcell, I think, brought. I think the Punches confirmed afterwards to our concept of how we're going to do the project, and we installed a flying scaffolding system off the temporary structure, and it meant that we actually had a building site on 3 layers. So we were actually putting in foundations, we were actually doing work to the columns, and we were actually doing work to the roof all at the same time. So normally a building site might be on a horizontal plane, but we actually had a building site with 3 different planes vertically stacked on top of each other. And the only way we could do that was to put in a scaffolding system that basically, so we had a full working site at probably 7 metres above the floor of the cathedral and about maybe 10 metres above the floor of the crypt. So we were putting in foundations when we were still doing work at 10 metres above it, and that was the only way that we could actually manage to get the first phase of the project completed, to get the plastering work started, to allow us to start doing the roof. But the temporary structure was used to support the roof.
The roof, okay. And was there temporary foundations then as well, or?
There was foundations below. One of the unique features with St Mel's, which probably, I suppose, you don't see until you go into the crypt, but below the blue limestone columns, there's actually a reverse arch under each column. So actually, as the load comes down under each column, it is actually transferred into an arch. And there's a masonry structure above that, which was still intact, and the temporary foundations to support the temporary steel structure sat on those reverse arch structure. Okay,
because there's always the fear that you're going to damage something with your temporary structure.
We didn't damage anything. I promise. It's all still there.
Yeah, great. Really interesting. Thanks.
Any other questions or comments?
Hello, Chris Southgate, consulting engineer. Congratulations to Gem Purcell, Design ID and Punch for a marvellous presentation. Thank you very much. My question is about possibly directed to Design ID. My question is, I was wondering to what extent the original Queen Post Truss structure would have complied with modern codes of practice. Do you have any sense from having analysed and produced a replica structure as to how the original structure might have? I'm not expecting an exact answer, but just a sense.
My technical guru on the right here is saying about the joints were the main thing that would have failed, and we find that we designed quite a lot of traditional king post, queen post, oak and other timber trusses, and it is generally the joints that don't comply. So traditionally you would have had mortise and tenon and a couple of oak pegs. As you notice in our presentation, we had introduced generally 4 number M20 bolts. So apart from that, the rest of it mightn't have been that far out.
I've actually got Lisa Eden, structural engineer. Very similar question. It struck me there that the stirrups that you put in at the end between the tie beam and the rafter, I think you implied that they were maybe not necessary, but were perhaps there to respect the visual of the original. And I just wondered why you didn't actually mobilise those in the design a little bit more rather than the M20 bolts.
I think that was back closer. I did look at them originally, and what they were providing was very insignificant in what we needed to get. Obviously, the load I think was something like 330 kilonewtons. The timber itself took about 100, and the stirrup would take 30 or 40, I think. So we were a long way off getting where we needed to be. So it kind of got ignored slightly from that sense. But
also, sorry to jump in, the biggest issue of that joint was the lateral shear that was being exerted along the plane of the glue lamb, and the stirrups, they didn't really do anything to resist. So we were taking probably about 60% of that lateral shear into the bolts, and they were it was being exerted as direct bearing onto the side of the glue lamp. So that's generally the reason.
Any question? Comments? No? Back.
Paul Healy from O'Connor Sutton Cronin. Again, like all prior to me, I'd just like to congratulate all speakers here this evening for a very informative and well presented evening lecture. My question again is probably directed to Design ID. In terms of the bottom tie cord, did you look to any other timber member sizes in lieu of the glue lamp?
We did. From what I remember originally, we were brought in to the contract with a very tight time constraint, and I think quite possibly that with those lengths and with the sizes that were actually needed, there was nothing else available. Glue lamp was the only thing. Maybe Kevin could maybe...
Yeah, no, at that stage, the decision probably had been made that glue lamp was going to be used. It was a case of kind of making it work rather than trying to go out and trying to find something that was going to work. So the glue lamp was something that Punch Consulting Engineer had brought on board from a very early stage in terms of the design, and it was brought through into the actual final design. So again, because time was against us in terms of coming up with an overall design and concept, the glue lamp beams were readily available, and they were ordered literally, and then there could be a slight design kind of slightly after we were going to do order, but we did an initial quick design calculation to ensure that the actual glue lamp was actually going to work, and then brought it further into the design later on.
If I might say, the original size wasn't a million miles away from the glue lamp member that was finally chosen. It was really a matter of timing, delivery, and a choice of material that could suit our program.
Lisa?
This is a bit of a curveball question. Water engineer, so I don't know how structural it is, but I am hoping to be singing in the church on Christmas Day. So my question is, to what end of thought came the acoustics? Because it's kind of hard for me to explain it, but there's and has been an extremely special acoustic in the cathedral, something I haven't seen replicated anywhere that I've, including St. Patrick's Cathedral in Maynooth. It's just, I can't describe it, and I'm wondering all of the extra stuff that's going on over the design above the aesthetic roof as such.
I suppose all of that timber would have been there. Again, I suppose all of that timber would have been there originally. You probably just never knew it was actually up above the level of the roof. So there would have been a huge timber roof structure above the level of the actual of the ceiling itself. In terms of you singing there, I can only know that the organ is being installed currently. It's taken 4 weeks to install it. And then probably the busiest time at the cathedral, he wants 5 weeks of complete quiet when he actually tunes this organ. So I'm assuming after 5 weeks of tuning it, at least I think the organ will be up to scratch for Christmas Day. I think hopefully, I'd say there might be a sing-song in it before then, just to make sure the acoustics actually work.
Just to make sure it makes you sound good. Very good.
Any other comments or questions?
Hi, Nuala Hayes, ACOM structural engineer. Just a query about the self-supporting arches that you used above. How does that work? Is it one single arch that you supported the other arches off, or they appear to look like cantilevers?
No, there's a lateral support at the top. I can very quickly go back and hopefully explain it.
Through all 207.
I have to, yeah. Just, you did enjoy it.
Pause on each one.
So, they didn't cantilever because there was a lateral prop at the top.
But there's a vertical load at the top as well. How is that taken?
If you look at the first and the last, that form essentially a semicircle. Yeah. They're propped off each other. Okay, yeah. So all the lateral load is the vertical support is provided by that complete arch. And then the other 4 radials are you've only got a lateral thrust at the top.
Thanks.
Believe?
Yeah,
Believe
I
me?
do. But actually, did you have any spreading at the bases of the arches? Were they fully fixed in?
Was there any spreading?
The walls didn't move.
No, because the walls, the support walls, I think at that point...
The walls on plan form a curve, and they're well braced. There was no fear of the walls moving anyway.
Yeah, okay.
So we, like, in analysis purposes, we designed that as a static pin support. You know, so
you took more restraint.
Pardon?
So there's more restraint in the arch rather than allowing a slide.
No, it's just that they're static supports, so that they can't. Well, exactly, they can't slide.
Yeah.
We were confident in working with the whole way through the process. Our calculations, design, our concepts were always passed through Punch Consulting Engineers, so it was a two-way process. You know, to ensure that they were happy it fitted in with their overall design ethos. And as Kevin says, the walls, combined with their thickness and the fact that they're curved on plan, they were capable to resist that force.
Great, thanks very much.
Okay.
Could I just ask one question? And that was the...
Hold on a sec, we'll just get the microphone.
I think it would just interesting to know the cost difference between Punch's original scheme of the steel roof and the onboard panola requirement for the Queen Post truss roof. And also the question is, was it a punishment or was it worth it?
Nobody's jumping up to answer.
The cost difference, significant. It originally started off as a steel truss, to be fair. The late Dr. Richard Hurley felt that because there was no original material remaining and that we were never going to see these trusses, that there was a significant argument that the cost benefit of using steel was worthwhile on a project like this, and that we could rightfully use the money elsewhere. That said, when I went on board Planola, and I think the first letter of objection that was received in planning, there was little or no resistance from us as designers to change it to timber, albeit it added a complexity that I think the lads have dealt with very well. Was there a last component to your question? Was it worth it?
Was it worth it?
For us?
I
suppose going back to one aspect, I actually, after having done it or carried out the work, I think in hindsight, on reflection now, I actually don't see another way out of doing it other than timber, because at least timber on site had the flexibility because of all the different parameters on site of varying heights and not parallel and everything. It would have been an absolute nightmare because every single bit of steel would have had to be surveyed to exacting dimensions, and then would have had to fit on site. So every bit of steel would have been different. There was far more flexibility on site with the timber work in terms of being able to manipulate it with the actual conditions on site that we actually had. I mean, if we were being honest, I think there would have been a huge amount of issues not known if we were using the original structure in terms of the fabrication of the steelwork and everything else, because every bit of steelwork would have been so different, and I think that would have had its own challenges in itself in terms of construction. So I think the timber as a means of, it ticked a couple of boxes. One, it solved an issue with onboard Panola. It obviously it met the requirements of a listed building in terms of maybe giving back something that was there originally, but also in terms of from a contractor point of view, I think it was a more flexible material to use in this particular scenario. I think even though we didn't go right down the road of the steelwork, I think there would have been a number of challenges with the steelwork which we probably would have had to overcome as well, but there would have been different challenges to the actual timber work.
Sparks would have been a challenge, wouldn't it?
Yeah, well, that's very true too, yeah. Very much so.
Well, the original design intent was only the structural truss itself would be steel, everything else would be timber. So you'd have had the same level of complexity with measuring each individual piece of timber.
Thanks.
John Mullins, structural engineer, consultant. What criteria did you use for the design of the masonry, for the lime columns and checking the existing masonry? There's not an awful lot of code of practices available to work to. So I'm just wondering how you actually designed the actual capacity of the lime columns.
To be fair, I suppose, okay, we had large stone sections. We knew the load capacity. We knew the load coming down on them. We effectively, the columns themselves were over-designed. They were oversized by a significant margin. But the real design criteria for us was the establishment of the joints, the spacing and thickness of the lead that we had between the joints, so that we ensured a smooth transition of load from one stone to the other, particularly as we were releasing the loads from the jacks, and the slow release of loads onto those columns, because we had a full weight of structure overhead.
Where did you dowel the drums?
No,
Or was
just
all just
dead load.
Dead load.
There's nothing at all between. We did find some evidence on some of the original columns where there might have been some timber pins. They might have been filled with some lead, but primarily, I mean, all the columns were removed was just purely dead weight on the actual vertical load in the column, which keeps them in position. I suppose we have introduced, maybe by connecting the capital stone to the top drum, we have actually made those as one piece. But other than that, everything is just purely axial load down to the actual columns themselves, onto the reverse arches. I mean, one of the things that Kevin didn't mention is literally the sequencing of the installation of the columns and the loading of the columns was something that Punches kind of carried like an underpinning sequence. Like, we just didn't go down one side. So there was like an underpinning sequence. So the columns were actually removed in a very much sequential fashion, and then they were installed in that same way. And when we had a number of columns then in position against Punch engineers, they gave us a criteria for releasing the original structure, taking out the temporary structure column by column, and releasing that dead weight back onto the original or the newly installed blue limestone columns themselves. And that probably on a column by column basis probably took up to a week. Like, it was very, very small amounts of weight and movement, and they were monitored on a weekly basis. So it was probably it probably took about the best part of 6 weeks to 2 months to transfer all of the original load back onto the new blue limestone columns, which again was going back into the original structure.
The microphone is roving again.
Thanks. Peter Cox from Carrick Conservation. Just to add to the two Kevins, or as I used to call them, Kevin squared. The stone we sourced, we set a very, very tight tolerance in any sort of problems within a natural stone, such as fissures or clay inclusions, etc. So there were months and months of research that went into visiting quarries to find a stone that was suitable for it. Just to add another little aside, when we did the historic research, and luckily all the paperwork was in the museum something like 6 weeks before the fire, but was taken out to be digitized, so all the paperwork survived. And we found this wonderful correspondence of a major row between the masons and the original architect, because the architect didn't want joints in his columns, but the masons didn't want to edge bed the stone. And there was this major standoff, and the final one was the bishop of the day asked the question, what's the problem? And when the architect said it was interior, so it wouldn't be weather that would cause a problem, the masons stood down. But in fact, they were proven right 150 years later. But hopefully there won't be another fire.
You know, no, everything that Peter said is correct. I mean, Peter from Carrick Conservation, they pretty much wrote the specification in relation to in relation to the stone for the actual cathedral itself. I suppose, I mean, and even go back to the amount of stone that was actually quarried to get the amount of stone we used. Like, there was 10,500 tons of stone for 675. I mean, the yield was very, very low. I mean, I think there was one particular, I mean, a week went by when there was about a 20 by 20 metre square section of quarry, about 6 metres deep, quarried, and out of that we actually got one type A stone, which is the base stone, which is the highest stone. And even when they were actually quarried and maybe they were brought back up from the quarry and there was a certain amount of work carried out to them, even at that late stage they would carry out a water test and you could find the slightest of fissure or crack in the piece of stone, and it's just put to one side because, again, from a structural point of view, it just couldn't be used. So I mean, there was, in terms of, I suppose, after Punch Consulting Engineers had looked at it from a structural point of view, and Peter had looked at it from an aesthetical, from the stone itself. Even after that stage, there was a huge process to get from the quarry to what you would consider a piece of structural stone you could use in I suppose in a structural capacity, which is probably, it's not something that's commonly used these days. You'd probably find there's a bit of steel in the middle and it's clad. So to get a true solid blue limestone column used in this traditional method, taking the loads that it was taking, which was substantial, you know, it's probably an achievement for the piece of stone that's there and will hopefully stand the test of time for the next period of time.
Well, I think that's a point that we might conclude on. It's been an extremely interesting evening, and certainly our experience in the Heritage Society is that usually by 9 o'clock a few people started to leave, but nobody left this evening, because I think I think that's a fascinating talk. It's nice for the Heritage Society to actually have occasionally, well, we try every year to have one conservation-themed lecture, and certainly tonight's presentation has more than set the record straight for that one. And I mean, 5 years work really coming to fruition. Hopefully we'll be singing on Christmas Eve. And yeah, definitely. And of course, I'm sure the cathedral will be absolutely packed to the doors. So well done, everybody. And could you show your appreciation for the presentation?